All right, so machine is learning, but how exactly? So we'll take supervised learning case and as an example. So let's say you have a data set, your D. It looks something like this: x1, y1, and x2, y2, so on and so forth. Right. Now, provided that this data can be represented in two-dimensional plane, if you graph it, let's say it looks something like this. Something like this, right? These are your data points. Now, when does machine learning comes into the picture? So you have the data and you know that there is a pattern in the data, like there exists a pattern in the data, and you cannot pin it down mathematically. But you believe that there is some function f of x. Let's say there is some function f of x that explains the behavior of the points or the data points, or it explains the relationship between the x's and y's. So you believe that there is some function f of x, and you cannot pin it down mathematically. You don't know it mathematically, but you have the data to learn from it. So that's when you use machine learning. That's when you use machine learning, and this is a form of a supervised machine learning, right? Because you have your response. This is the response, scalar response, which are the output or the dependent variable, and this is your independent variable. X's are the independent variable. So basically, you have a function f that maps all the x's to y's, and y belongs to a real number since it's a scalar, and you can take any number of inputs. So in our case, we're dealing with simply two dimensions. So x in our case belongs to the real number line for now. So what is the meaning? Like, what do I mean by there exists a pattern? So if you look at this picture carefully, this graph, just a sec. Yeah. So if you look at this set of points, then what is the one thing that is common between all those points? Well, someone can say that they look like they lie on the curve y equals sine x. Like, if you join these 2 points, they represent the sine curve, right? And that is your f of x. Like, you believe that there exists a pattern, and that is your f of x, right? Or you don't know that whether it's exactly a sine curve, but you believe that, well, there is a function f of x that represents this whole data set. Now, your job is to find this function f of x, like what this f of x is. So how are we supposed to do that? We will do that using a hypothesis set. We will first build a hypothesis. So looking at the nature of this curve, looking at those points, the data set, we can make an educated guess that, well, maybe some sinusoidal function, for example, maybe h of x, maybe h of x is a sine bx, maybe h of x is a sine bs. So this is a hypothesis set because a is a variable, a is a constant, but still it's a variable. And as hypothesis, this is a hypothesis set h of x, but a specific hypothesis will be, let me represent this as capital H. Specific hypothesis will be sine 3x, right? This is a very specific sine curve. That is one hypothesis. And then you might have another hypothesis, which is, let's say h2x, that is 3 sine 4x. That is also a very specific sine curve, right? So the point I'm trying to make is, your hypothesis set consists of small hypotheses. That seems to be quite logical in it. Like, your hypothesis set consists of your h1x and h2x and so on. So now from this hypothesis set, you have to pick the one sine curve that represents this entire data set, or you can say that approximates f of x well. So that is the approximation, like the linear regression, the curve fitting problem. You have your data and you have the hypothesis set. From that, their hypothesis set, you pick one such that it approximates f of x well. And how can you know that it is indeed that the hypothesis that you chose is indeed approximating f of x well? For that, there are different metrics to use. One of them is MSE loss, which is MSE is the mean square error. You find the um, square distance of the response of the predicted value, which is the response given by your hypothesis, and the actual ground truth, which is the response given by the function f of x, which is called the target function. This is also known as target function. Right. So there is one MSE loss. Then there is MAE loss, which is root absolute error, which is not root. It's basically it's absolute error, mean absolute error. So it's basically the modulus of the difference between the responses of the hypothesis and the target function. So, so this is a classic, machine learning problem. It's a curve fitting problem. It's basically a linear regression, and most of the machine learning tasks have this sort of a mapping where they have, in our case, we have only one single real number as an input, but in most of the machine learning tasks or the deep learning task, you might have n inputs. You might have n real numbers as an input vector, or a vector of length n, and that maps to a single scalar value on a number line, on a real number line. So basically, you have a function f that maps from Rn to R. So this is a typical machine learning relationship. So if there exists a relationship, then only you can go ahead and search for the relationship. If there is no pattern in your data set, then it's pointless to you apply machine learning technique. So that's that. I hope I was able to clear what is machine learning in essence, and what is hypothesis set and what is hypothesis. So now the thing is, how do you approximate this f of x? Means, how do you navigate through your hypothesis set? How do you search for the particular hypothesis which fits the curve best, which means which fits the dataset well? So how do you figure out that? Well, there are very many optimization techniques. So you create an optimization metric. For example, this MSE and all this is an error basically, and then you use an optimization technique. Most famous is gradient descent algorithm. So if you gradient descent algorithm, what it does is, before that, let me just go into this thing which is known as navigating through the hypothesis. So hypothesis set, what do I mean by that? So you have your hypothesis, let's say sine 3x. It may look something like this. So sine 3x may look something like this, which might not be the ideal representation. And if you use sine 3x, that might look something like this. These two sine curves are different. So this is sine 3x, 3 sine 3x, and this is your sine 3x. So you can see that 3 sine 3x is a better 3 sine 3x is a better representation, right? So that is one hypothesis. So what you have is, you can change a and b. These are the metrics. This is the parameters, and x and y's, those are given on the data set. So basically, f is a black box. X is given as an input, and you get the corresponding result. So you have x and y. You have to figure out this f. So we first guess the function. We call it g of x. Let's say g of x is our guess, and then we try to take the difference between the response and the actual response and the predicted value, and try to minimize this equation. So if this L or error, let's say if this E is less, the lower the E, the better is the hypothesis, like the approximation. So for lower values of a, you will get better hypothesis. So our goal is to minimize this e. In machine learning literature, minimize the loss function, and for that you have some famous algorithm like gradient descent, then RMS gradient descent with uh, RMS prop, and then momentum, and then AdaGrad, and then Adam optimizer. So you have this kind of optimizers. So ultimately, it boils down to an optimization problem. So in optimization problem, you change what? You change these A and B. So if you change A and B, then only you are just navigating through the hypothesis set. That is all. But you have to navigate through it properly. Like there should be a direction, and that direction is given by the gradients. Hence, in gradient descent algorithm. So I hope this idea, which I explained, rather I discussed. I hope this idea is clear, and I was able to make you understand what actually machine learning is, and mathematically. So, all right then, that's it.